Hello there. To understand and predict the bonding in materials, it's very important to have a good grasp of the electronic structure of the atom and understand the connection between electronic wave functions and atomic orbitals. This four-part series of videos are presented at a level suited to a sophomore student taking an introductory course in materials science and engineering, who's already been exposed to the basics of the quantized nature of the atom, perhaps in a freshman chemistry course. In this first video, we begin with a general overview of quantum numbers, and then talk about the electron wave function, psi. In particular, the amplitude of the wave function, as well as its sign, which we also call the phase. And we'll get into the probability density, which is psi squared. We then focus on visualizing the wave functions using orbital pictures. And the second and third videos explain how we can represent the radial and the angular components of the wave functions in separate pictures. The last video will then focus on the energy states of electrons in the atomic orbitals, how they change across the periodic table, and how those changes in turn can be used to understand the periodic trends in atom size and electronegativity, which are critical in predicting the type of bonding exhibited by a material in the solid state. I hope you'll find these videos useful to you. Let's just begin with a short overview of what I'm hoping everyone has seen before in freshman chemistry. So electrons have wave-like and particle-like properties. We're going to focus on the wave-like properties here. They diffract light, and they also occupy orbitals. And here are some of the orbital pictures shown on the right. The S, the P's, the D's, that we'll get into later, but you should again have seen before. Orbitals represent the space in an atom occupied by an electron. That space is described by wave functions, and the wave function is called psi. Psi has amplitude, it has nodes, and phase, and it represents the probability amplitude of the electron. Psi squared represents the probability density, the probability of finding the location of the electron in a given point or at a given radius of that orbital. The size, the shape, and the orientation of that probability density and of the wave function itself is determined by quantum numbers, which again you should have seen before and we'll very briefly review here. First, the principal quantum number n. This really dictates the energy level, but not entirely, as we'll see later. So this represents the size, or the average distance from the nucleus of the electron in the orbital. It can have values of 1, 2, 3, etc., which sometimes are called the K, L, M, and N shell. The next important quantum number is the L, the orbital quantum number, sometimes called the azimuthal quantum number. L represents, or its meaning is the shape of the subshells. And we'll see also later it represents the angular momentum. L can take on values of 0, 1, 2, 3, up to a maximum of n-1. And these numbers are usually replaced by letters. So for L is 0, we call that the s orbital, L is 1, the p orbital, L is 2, the d orbitals, L is 3, the f orbitals, etc. With respect to the shape, then for the L equals 0 s orbitals, they're spherical. The p orbitals are ellipsoids. M sub L is the magnetic quantum number. This actually represents the orientation and the multiplicity of the orbitals of a given L. M sub L can range in values from plus L to minus L, and its multiplicity is 2L plus 1. Let's take a simple example for the p orbital, which has L equal to 1. And so the values of m sub l could be +1, 0, and -1. And so there's three possible p orbitals, the px, the py, and the pz. And so this ellipsoid has three possible orientations associated with those major Cartesian axes. And finally we have the spin quantum number, m sub s. This is not so much a property of an orbital, but the property of an electron. It could have spin up or spin down, which in turn takes values of +0.5 or -0.5. And so in the end, from all of these quantum numbers, we can sketch the orbitals and their orientations using boundary surface diagrams. And so these sketches here really represent the electron probability distributions, both their radial extent and their angular dependence. So that was just a brief overview of quantum numbers and wave functions. But for the rest of this module, we'll go into things a little bit more slowly and with a little bit more detail. So let's take a closer look at the electronic wave functions. Symbol is psi. So psi is the wave function of the orbital, and we're going to see the equations for it can be a little bit intimidating, but for now let's just consider a regular sine wave, oscillating here as a function of distance from the nucleus, r. Well, I think we're comfortable with the fact that a wave has amplitude and phase, or the sign of the wave function. So in this case, the wave function is positive here and negative down here. This particular wave function also has nodes. Nodes are simply where the wave function itself has no amplitude, such as these points highlighted here. And at a node, it changes sign. It goes from a positive sign to a negative sign. So the positions of the nodes are also of particular importance. Again, that's where the wave function has no amplitude. Psi squared is the probability density, the likelihood of finding the electron at any particular position. It is the square of the wave function. So here I've taken my sine wave, squared it, and of course all of the resultant amplitudes are positive. But it still has nodes. So we note here, in this case, psi squared is 0. What does that really mean? That means there is no chance of having any amplitude at that particular value of r. And when we relate that to an electron, it means the electron has absolutely no chance of being at that position. Where is it? It could be anywhere else, represented by the different probabilities. But the nodes are significant because there we know it has no amplitude, no probability density. We do know, however, that the sum of the probability over all space must be 1. So the sum of psi squared equals 1, meaning that we've got 100% probability of finding the electron somewhere. We just don't know exactly where. But again, we do know where it is not. Well, this is just a simple sine wave. We could consider a slightly more complicated function. This is a damped sine wave. The details don't matter. But again, we see the wave function has amplitude. It has nodes. It changes at a node from a positive sign to a negative sign. And in this case, the amplitude just becomes less and less with the distance r. This is psi squared for this particular function that I showed up here. Squaring it, same thing as the previous one. Now psi squared is positive everywhere. That represents the probability of the electron being in this particular place. We still retain the nodes where there is no probability. Our orbital wave functions, deduced from quantum mechanics, they're a little bit more complicated.
and I show them here for orbitals varying from the 1s through to the 2pz. We can separate the wave function into two components. One is called the radial component. That is how the amplitude of the wave function varies as a function of distance from the nucleus. We'll call this r. Then we also can separate it into an angular component. We call that y, and this is how the amplitude changes with angle. So this would give us the shape and orientation of our orbital. As we separate into these two components, then we're using polar coordinates, which comprise of distance and our two angular functions. Let's not worry too much about those at this stage. Well, to visualize orbitals, we want to see how this radial function changes with distance. The radial function depends on the principal quantum number n and also the orbital quantum number L. So again, the radial function represents the change in the amplitude probability of the wave function and its sign with distance. The angular function, this represents the angular dependence of the wave function. It's actually what's called a spherical harmonic function. And in this case, this would show us how the sign of the wave function could change with angle. And it's possible that we could have nodes in the angular function, which are called angular nodes. In the next video, we'll use some specific examples to clarify these different nodes.